Hello, chemistry students. We are continuing our conversation about energy involved in phase changes, and we have discussed the concept of the heat of fusion. I'm just going to say H of fusion, delta heat is that enthalpy we've used before, and that's for water. We know that it's 80 calories per gram. We know the heat of vaporization for water, which is unique to water. All these are different, and we'll talk about why in our next lecture, is 540 calories per gram. And we know C, the specific heat for water. So basically, C is specific heat, or specific heat capacity for H2O is 1 calorie per gram degrees Celsius. And so I kind of wanted to talk about those concepts a little more and show you a little bit about how those calculations might look. So in this first question, basically, we have two beakers. We have two different substances, X and Y, and they were at the same initial temperature. And basically, we are adding, so it says which compound has a higher specific heat, which compound has a higher specific heat if heat, the same heat was added for both substances, and we'll say the same amount of heat, so over time it was exactly the same. So essentially, it's kind of like we put that on that hot plate we were talking about before, right? And we turned it on, and we plugged it in, and we just added energy, right? So we added a bunch of energy to this, like we talked about with the ice before. So we add energy, and they heat at different rates, right? So one heats more easily than the other. So what that implies is the specific heat of this substance must be lower. It's easier for the energy to warm the substance up, and this must be a higher specific heat because it's harder, right? It's harder for that substance to heat. That's that thermal inertia we spoke about before. So basically, the slower the less the substance heats up, the higher its specific heat is. Okay, so let's sort of look at that. We can kind of do some calculations with that in this question right here. So it basically says how much energy is required to heat 50 grams of water from 15 to 50 degrees Celsius. So I want you to think about what that might look like. So I'm going to go back to our diagram. So basically, we can use this diagram because we're talking about water, and we're saying, well, we're right here at 15 degrees, and we want to warm our substance up from 15 degrees up here to 50, right? And so this is going to tell us how much energy it's going to require, right? So we want to go from 15 degrees to 50 degrees. So the calculation that you need for this is heat is equal to mass times specific heat. I should write that better. Let's just write, I'm going to use C for specific heat. Times the change in temperature. So basically, you're going to multiply those three things together, right? So if you think about specific heat for water, it's 1 calorie per gram degree Celsius, right? So we need to have 1 gram and 1 degree Celsius, and so that calculation makes a little bit of sense. So for A, we're going to take our 50 grams of water, we're going to multiply it by 1 calorie per gram degree Celsius, and then we want to look at our temperature change, right? So this is delta T, and always with delta T, we're always going to do the final temperature minus the initial temperature. So we're going to take 50 minus 15, and that's going to be the heat involved in that process. So 50 minus 15, that's kind of a not so bad calculation. That's 35. And then we're just going to take that and multiply it by 50. So when we take 35 times 50, we get, we get 1,750 calories. And if you look at it, right, I want you to notice that all the units cancel. Grams cancel with grams, and calories cancel, or Celsius cancels with Celsius, and we're left with calories. So when we look at our diagram again, this phase change right here, basically, this is that energy that we were adding from our hot plate. So it took us 1,750 calories, right? And if we put that into food calories, kind of interesting, remember, this would be 1.75 food calories. So we can kind of think of it that way. Okay. So I'm going to let you guys do the second one, and I've written down, it says how much energy is lost, right? So this is gain because we're heating it, right? So that's gain, so that's in. And so this is lost. We have to cool the aluminum down, and we want to take it from 125 to 50. The calculation is going to be the same. The heat involved is going to be the mass times the specific heat times the change in temperature. And I took the liberty of looking up the specific heat for aluminum on the internet, so that you can see is much lower. And you might know that metals conduct electricity really well. And you might know this because maybe once upon a time you left a spoon in a pot on the stove, and you grabbed hold of it and you went, oh, that's fairly hot. And that's because metals are good conductors of heat because they have a very low specific heat capacity. Okay, so I'm going to save that one for you guys to work on. So I'm going to ask you guys to do B, and I will put those answers up as I upload this content to Canvas. I want to show you another example of how this might show up. So basically, when we are changing the phase, so I'm going to go here and just kind of talk really quickly. When we're in these places right here, right, you'll notice that there is no temperature change. And so the calculation at that point is a little teeny bit different. The energy involved in the phase change is a little bit different calculation here and here. And so let's write that down too. I'm going to put it right in the same place. So when we're doing a phase change, this is when we're changing temperature. When we're doing a phase change, the calculation is a tiny bit different, okay? The heat is going to be the heat of fusion or the heat of vaporization times the mass, okay? So when we want to calculate that, we're either going to use heat of fusion or heat of vaporization, depending on if we're boiling the water, condensing the water, melting the ice, freezing the ice, okay? So let me try to show you that one really quick. So I'm going to take this question right here and go through this one with you, and I'm going to save the other two for you, okay? It says, how much energy and calories is needed to melt 45 grams of ice at 0 degrees Celsius and then warm it to 55? What's really cool about this is you can actually follow this process on the phase change diagram. And so I'm going to try to show you that in another picture here. So we're going to write out that phase change diagram again, where we know that we took our water from 15 to 0, we melted it, we took it to 100, we boiled it, and we got it to that high temperature, right? So this was 0 degrees Celsius, and this was 100, right? This was our temperature, and this was our heat. So what's cool about this is you can actually see this, right? So what we're going to do in our question, if we go back to it one more time, it says we're going to start it with ice. So we're starting with solid ice at 0 degrees Celsius, and we're going to change it into liquid, and then we're going to warm that liquid up to 55 degrees Celsius. So we're going to do two calculations here, okay? We're going to take that 45 grams of ice and melt it, okay? And then we're going to take that water at 0 and warm it up to 55 degrees, right? So there's going to be two calculations there. So remember, our phase change calculation, right, is going to be either the heat of fusion or the heat of vaporization, right, times the mass. And then when we're heating the substance, right, when we're heating it, basically, that's going to be the mass of the substance times the specific heat times the change in temperature, okay? So we know in our case that we have 45 grams of water, and it's at 0 degrees Celsius. So we're going to do that one calculation, and then we're going to take that 45 grams of ice and we're going to warm it up from 0 to 55 degrees Celsius. Okay, two calculations, okay? Our first calculation right here, okay, is the phase change calculation. So we're going to take heat for this reaction is going to equal the 45 grams of water multiplied by 80 calories per gram. That's our first calculation of melting the ice. Our second calculation is going to be take that 45 grams of water, multiply it by 1 calorie per gram degrees Celsius. Remember, that's unique to water. It will change for other substances. And we're going to multiply it by 55 because it's 55 degrees Celsius minus 0. And when we add those two numbers together, we're going to get the heat involved. So we're going to take our 45 times 80 to get 3,600 calories. And we're going to add that to 45 times 55. and that's 2,475 calories. When we add those together, we get the energy involved in this phase change, 6,075 calories. So basically, to take that ice at 0, to melt it, that's this calculation, and then to warm it up to 55, that's this calculation, it takes this much energy, or 6.075 food calories, right? Okay, so basically, I'm going to leave you to it. I'm going to let you guys work on this one and this one. Just remind yourself that in this question, it says how much energy is released. We're taking that water and we're cooling it back down. Interesting question. And then this is a hard one right here. You're going to take that steam, you're going to condense it. So you have to take steam, condense it to 100, and then cool the water to 0, and then the frozen water is put into ice. So basically, when you look at this calculation, C, I'm going to let you guys do this. You're going to start up here. You're going to condense your steam, you're going to cool your water, and you're going to freeze it. So you have 3 calculations that you have to do, okay? You have to do this one, and this one in order to get that correct. Okay, good luck on that. I will write these answers out for you and put this up on Canvas for you. Thank you so much for listening. Hope you're having a great day.